Good afternoon, students. Let's begin our new lessons. In this lesson, we continue to discuss the assignment problems. But in this lesson, we focus on solving assignment problem by Hungry method. The assignment problem is a special BIP problem, so it can be solved by branch and bound method. But a specialized algorithm is designed by Hungry mathematics. It solved the assignment problem more efficient. We call it Hungry method. The algorithm operates directly on the cost table for the program. More precisely, it covers the origin cost table into a series of equivalent cost tables until it reaches one where an optimal solution is obvious. And we noticed in assignment, the objective function is minimize greater than or equal to 0. And the 0 is the minimized value. If we can retrieve the 0, we will achieve the optimal solution. So if all the assignment can be made to the 0 element positions, the assignment is clearly optimal. The question remaining is how to convert the origin cost table into the table which at least include one cell in each row and each column. For example, in this table, we must to convert the origin cost into the include one cell in each row and each columns. And for example, in this row we minus 11. In this row, we minus 13. In this row, we minus 5. And we can get 0 in each row. And we notice the special precision in assignment problem. The key to this conversation is the fact that one can add and subtract any constant from every element of a row or column of the cost table without really changing the problem. That is, an optimal solution for the new table must also be optimal for the old one and conversely. Now we give the proof of the proposition. We notice that we denote by assignment is original and we set Bij equal to Cij plus Ti plus Dj, and we note this is the new assignment. And we calculate the new objective function is J equals sum from I to n, sum from j to n, Bij Xij, and Bij is this formula. We put it into this formula. We get this formula. And we divide into, and we get that. This is the constraint, and equal to 1, So we get equals to J plus sum from I to n Ti plus sum from j to n Dj. And this is the constant. So we notice that this objective value and this objective value difference only constant. So these two problem or these two assignment problem is the same solution. According to the precision, therefore, the algorithm begins by subtracting the smallest number in each row from every number in the row. This row reduction process will create the equivalent cost table that has a 0 element in every row. For example, in this table, we minus 11, this row minus 13, this row minus 5. And we remember this example is the job shop example, and the machine is 3 and location is 4. So the machine is less than location. So we add doom machine, that is 4 machine, and the cost is 0. So the machine, the number of machine and the location of machine, the number of machine and the number of location is equal to. So we abstract 11 or this abstract 13 and abstract subtract 5, and we get this row, this row, this row. And we note that in this table, there is at least 1 0 in each row. Each row, and each row. Each row is at least 1 0, and we can choose the 0 cost to install the machine, and the total cost will be 0, and we'll retrieve or we'll get the optimal solution. So if the cost table has any columns without a 0 element, the next step is to perform a column reduction process by subtracting the smallest number in each column from every number in the column. Therefore, the new equivalent cost table will have 0 elements in every row and every column. So in the last table, we can choose this 0, this 0, this 0 is 0. That is x 1 4, x 2 3, x 3 1, x 4 2, and this variable is equal to 1. That is, we choose these locations to install the machine. It means machine 1 installed location 4, machine 2 installed location 3, and machine 3 installed location 1, and machine 4, and it is doom machine, installed in location 2. And the new assignment objective value is 0. And the 0 is the optimal values. So we get the optimal solution. That is the optimal assignment in this program is machine 1 installed in location 4, machine 2 installed in location 3, machine 3 installed in location 1, and no machine installed in location 2. But the objective function of the orange assignment is we feed back the optimal arrangement to the orange programs, and we circle this, and this. We get the total cost is z equal to 11 plus 13 plus 5 plus 0, and this is 29. This is the program's minimize cost, and the circle is the optimal solution or optimal assign of these programs. This is the solve of this program. So from these examples, we notice that unfortunately an optimal solution is not always obtained quite so easily, as we now illustrate with assignment program formulation of operation 2 for the better product combination programs. And we remember the table in better product combination operation 2. In these programs, there are 3 branches. That is, the assigning is 3, and the task is 4. So the task is not equal to the assignings. So we added doom column. Doom column is doom task, and set the cost is 0. And so the task is failed. So, and in these programs, branch 1 can do 2 tasks, and branch 2 can do 2 tasks. So we set 1A, 1B is branch 1, 2A, 2B is branch 2, and each requests 1 annex. So in this table, the annex and the tasks is the sum or equal to. So this is the general assignment programs. Now we notice in this table, each row has 1 zero, and this row have no zero too. So we minus 714. And we notice that each column has no zero. So in each column, we minus the smallest number. The smallest number is 810 minus 810 and minus 814. And we get this table. In this table, we notice that each row and each column has 1 zero. So we control assignments, and we circle this and cross out because this is impossible. And we circle this and cross out this, and circle this and cross out this. Cross out means impossible. Because in this table, we notice that the circle is 3 and not less than tasks or less than assignees. So the assignment problem is not finished solved. And we continue solve the procedure. The creation of additional serial elements. That is, in these problems, we need to create additional serial so we can try assignments. The idea involves a new way of creating additional position with serial elements without creating any negative elements, rather than subtracting a constant from a single row or a column. We now add or subtract from a combination of rows and columns. Step 1. This proceeding begins by drawing a set of lines through some of the rows and columns in such a way as to cover all the cells. For example, in this table, we draw the minimum set of lines cover all cells. This line cover the cells in this table. And we note that there are some numbers not covered by the lines. So we choose the smallest number, and the uncovered is subtract this number. And the covered column plus this number, we get this table. Means that we choose this is the smaller number, and this row minus 13, minus 13, minus 13, minus 13. But in order to keep 0 is also 0 too, so we plus 13 in this column, plus 13 in this column. This is the proposition. Keep the solution is not changed. So we get this table, and in this table we notice that there are more cells in these tables, so we can choose more. And now we try assignment. Assignment 2. We circle this, circle this, circle this, circle this. And when we circle this is impossible, we cross out. And we circle this is impossible, cross out. And we circle this is impossible, we cross out. We so this is impossible, so out. And means that. But we notice in this table, the circle is full. The circle 1, 2, 3, 4. That is this assigning, and this task is not successfully assigned. So the problem is not a finished solution. So we continue the solution. We continue the proceeding, and we draw the line to cover all series. We draw this line, cover all series, and we note that this is the smaller number, and in this row we minus 13, and in this column plus 13 is in order to keep this 0 is 0, keep this 0 is 0, this 0 is 0. So we can get this table, and in this table we notice that there are more zeros in this table, so we can choose more, and we try assignment again. We choose this, and this is impossible, we cross out. This is impossible, cross out, and choose this, and the sum row and the sum column is crossed out because it is impossible. For example, when you choose this, and this is impossible. When you choose this, and this is impossible, and when you choose this is impossible, and when you choose this is impossible, and when you choose this, it's impossible, and that is. Now in this table, we count the circle. The circle is 1, 2, 3, 4, 5, and the circle is 5. Means that all tasks is finished assignment, or assigning is finished assignment. So we get the optimal solution is assigning 1A is finished task 2, and assigning 2A finished task 1, assigning 1B finished task 3, assigning 2B finished task 5, and assigning 3 finished task 4. So all tasks is 2 finished, and all assignments is 2 successfully assignments. So the problem is successfully finished, and we get the optimal assignment is x1 2 equal to 1, x2 3 equal to 1, x3 1 equal to 1, x4 5 equal to 1, x5 4 equal to 1. And if we need to calculate the objective function, we feed back this optimal solution to the orange cost table, and we get that this is the assign, this is the assignment, this is the assign, and this is assign. And the objective function is the total cost, J equal to this plus, and it is the 3,219. This is the total cost of these problems, and we get the optimal solution of this problem and the minimum cost of this problem. So we finish the solution of this problem. Now this is the solve procedure of Hungry method. Now we summary the Hungry method action. It is include step 1. Subtract the smallest number in each row from each number in the row. Step 2. Subtract the smallest number in each column of the new table from even number in the column. Step 3. Test whether an optimal assignment can be made. You do this by determining the minimum number of lines need to cover all cells. If the number of lines equals the number of rows, an optimal set of assignments is possible. Number 4. If the number of lines is less than the number of rows, modify the table in following way. A. Subtract the smallest uncovered number from each uncovered number in the table. B. Add the smallest uncovered number to the numbers at intersections of covering lines. C. Number crossed out but not at the intersections of crossed out lines carry out unchanged to the next table. Step 5. Repeat step 3 and step 4 until an optimal set of assignments is possible. Step 6. Make the assignment one at a time in position that have zero elements. Begin with rows or columns that have only one cell. Since each row and each column needs to receive exactly one assignment, cross out both the row and the column involved after each assignment is made. Then move on to the rows and columns that are not yet crossed out to select the next assignment. With preference again given to any such row or column that has only one cell that is not crossed out, continue until every one and every column has exactly one assignment and so has been crossed out. That's okay in these lessons. Thank you very much.